Welcome, Juliet.
Thank you, Doug. Good morning. It's really lovely to be here today. I'm very excited to be talking to this audience. I've had a chance to talk to some of you, and you clearly have great experience and high-quality questions yesterday that in conversations I've had. And so I'm really happy to talk about Spark and MLlib. I always like to do a quick poll to understand what people are interested, where people are at. So let's start with who has a right hand. About a left hand? Cool. Who's used Spark before? Who wants to use Spark? Who is interested in machine learning? Who does machine learning professionally? Yeah, this is gonna be so much fun. Great. So today we're doing an introduction to Spark and to MLlib. So what exactly am I going to be talking about? It's a pretty broad topic, lots of things we could do. I've broken this up into two pieces, where the first part I'm going to explain how Spark works and its execution model, so we can understand why it's useful for machine learning. And then I'm going to discuss how to use MLlib by giving a concrete example. And there's actually a GitHub repo that I'll point you to at the end if you want to go download this concrete example. It has little exercises in it, so if you want to expand on it. This whole talk is sort of based off a tutorial that I've given before. So hopefully if you're interested and you want to learn more, there's great resources for you. So as promised, I'm getting with the Spark overview. So you all obviously know about Spark, excited about Spark. The reason that Spark has become very exciting for a lot of our customers and users is that two things. It's easy to develop and it's really fast to run. So parts of it that make it easy to develop is that its API is very slick, very clear. MapReduce is very well defined, and you have clear life cycles between the map phases and the reduce phases, but it's maybe incredibly verbose. And it's only written in Java. And so not everyone that wants to be able to use huge data sets wants to write that all in Java in such a verbose way. It can be very limiting and somewhat slow. And so many people that I work with are excited about the clean API of Spark and the multiple language bindings, particularly Python. So the examples that I'll show later are all written in Python. The machine learning library APIs and the APIs across Spark multi-language bindings are very, very similar. And so if you see this and you're like, but I want to do this in Scala, I want to do this in Java, great, it's look pretty much exactly the same. Another aspect of this is that Spark provides an interactive shell. So this is nice if you want to do a little experimentation with your Spark code, but particularly if you're a Python user. Who's a Python user here? Me too. If you're a Python user, sometimes it's nice to work in notebooks to do a little bit of experimentation so you can grab some data, do a little bit of plotting and see what's happening. And Spark really enables you to do that because of its interactive REPL mode. And so some of the examples in the tutorial that I'll point you to at the end is actually built into an IPython or Jupyter notebook that you can launch and attach to a Hadoop cluster and use data in it. So hopefully this will all hang together really well. It's fast to run. Its execution model makes it fast. Spark tries to pin data that it's working with in memory. So one of the biggest bottlenecks in general in big data analytic workflows is disk I/O. Reading off of a disk, writing to a disk tends to be really slow because usually the disks actually have to spin. There's a physical limitation as to how much that's really going to work for us. So that's core Spark. Another aspect of Spark that makes Spark incredibly appealing is the ecosystem. So when people refer to Spark, Spark is actually a collection of a ton of projects. The ones that I see the most used in our customers and generally people that I work with as other data scientists in the Bay Area is Spark SQL/DataFrames. People that use Spark SQL and think that they're going to get some quick queries out, they're like, oh, my Spark SQL query takes 30 seconds to run. And you're like, well, you are launching a Spark application that needs to start up JVMs. But the really beautiful and useful part of Spark SQL is that it lets you express some of the operations and data cleaning that you need to do to your data sets in a SQL-like language. And it has a very constrained version of what data you're representing, because SQL is really about tables, and tables are really about schemaed collections of data. Obviously, a very important part of what makes Spark really exciting is the machine learning libraries that are being built on top of it. And so particularly there's Spark MLlib, which is the example I'll be talking through today. And of course, there's also Spark streaming for the cases where you need real-time ingest, like Ivo was talking about earlier. So in general, what Spark looks like in CDH and how this all hangs together is that you have some data at the bottom, you have a resource negotiator that handles getting compute resources for you, and a few different components of Spark that you can use that sit on top of core Spark and use those core APIs to accomplish different tasks. And on top of that, in my world, when I go and talk about Python, PySpark a lot, is a layer of Python API on top of those things that you can then use. So let's get to the Spark execution model and why it might be an interesting and useful model for us. So I have a really short Spark program here. And what I want you all to sort of grok and understand is that when we write a Spark program, we write a driver program. And what's happening is that we're describing to Spark the sequence of operations we want applied to our data. And the Spark driver program is then going to orchestrate what needs to happen on the worker nodes. So the worker nodes are the ones that are often right next to the data that you actually want to read in. And those worker nodes, when the Spark driver node says, hey, you all need to wake up and do some work for me, they wake up, they set up an executor, and executors are the things that do the operations and apply functions to records inside of your data set. And the records inside of your data set are split into multiple tasks. And so this is where the parallelism, or one aspect of the parallelism comes in, is that on a specific node, you can have multiple threads reading these tasks and processing them. So what ends up happening is that we have this concept of an RDD. And an RDD is sort of the abstract concept of what a data set is in Spark. And so what Spark ends up doing is saying, like, okay, I know that this RDD we're going to apply a function, then the next RDD we're going to apply another function, and it begins to build up a graph of operations that you want to execute. And then you have to actually tell it to execute. And so when you tell it to execute, Spark will look at the DAG, the graph of operations that you just defined, and try to combine it into the smartest possible small set of operations. This is called lazy evaluation. I really hope I'm the only person that has a puppy picture today. I'm kidding, I don't hope that. Maybe next time everyone else will get puppy pictures too. So lazy evaluation is really useful for us because it lets us defer what the actual physical operations that are going to happen on the system, or making decisions about what the physical operations that happen on the system, until we've fully described our data flow. So because there's lazy evaluation, you can run into a lot of funny problems. Sometimes I get customers who are like, my Spark job doesn't execute. Really? Show it to me. They show it to me and it's like, well, it's because you didn't tell it to execute. And I'm like, what do you mean? I wrote a Spark program and I submitted it. What you have to understand about lazy evaluation is the distinction of two types of operations that you can apply to your RDDs. The first are transformations. These are just abstract descriptions of how you can turn one RDD into another. And the easiest way to distinguish transformations and actions is the type that is returned by the function. So map means let's apply a function to each element in our RDD and create a new RDD. Similarly with filter, but you might get a smaller RDD. So transformations return RDDs. Actions are the things that actually require something being returned in order to happen. If I say collect, that means, hey, Spark, return the entire RDD to the driver node. Or count this. Count returns an integer. Collect returns, well, it depends what language you're writing it in, but it returns something in the language you're writing it into the driver node. And so those are not RDDs, and that's the easiest way to distinguish this. And so in the case of the machine learning library, slightly less clear, but things like model training, the returns model, meaning there has to be something actually fit and that model itself is not another RDD, that's an action. So that's a good distinction to keep in mind. Let's work through what this actually means. So let's say we have a file that we want to read in. It's a CSV file. And then we're going to apply a few functions to it. So let's say I had some CSV file that represents a time series. And I've written a function that can take a line from a CSV and turn that into something that's like a time series, and then another function that takes something like a time series and identifies with a Boolean whether or not there are outliers in that time series. And then I want to count how many outliers time series I have in my entire data set. So what I'm going to do is that I have a file living in HDFS. I wasn't the only one that heard the popping, right? Yeah. Okay, good. Slowly start losing it during a talk is always my goal. So we have a file inside of HDFS. And what we're going to do is we're going to read, this file lives in separate partitions on our cluster, and we're going to read this into an RDD. So we read it from disk, into memory, into Spark's model. So get our Spark context, and we say, OK, we know this is a text file format. Read this in for me. So that creates an RDD around those partitions, and it's now in memory in Spark. I'm then going to map and apply that to series function. So my partitions used to have lines from a CSV, and now they have something that's closer to a time series. And I apply my function, filter out the parts that I don't want, and I count. This is a very simple workflow. We can really easily see how Spark could optimize this, right? So instead of having different stages between these, it could apply both the transformation into a series and to a filter once, instead of making 2 passes, even in memory, but 2 passes over the data. So Spark is doing smart optimizations and compilation of the graph of operations that you want to do, and you don't even have to think about it. This is really nice because realistically, your Spark operations look something more like this. This is especially true if you're doing feature extraction and machine learning model training. And so the types of operations you do can look complex, and this is, I would say, is even relatively simple. Because in machine learning, especially with really large data sets, what you find yourself doing when you train a model is doing iterative operations over it. So you take pass after pass and you slowly try to converge to something. This is, again, really slow if you're writing to disk and reading from disk between each iteration. And so we're excited to use Spark for machine learning now, right? I am. Great. Now we're all going to pretend that we work for a telecommunications company. And we're tasked as one of their data scientists to predict churn in their user base. We have a group of customers. They are all subscription customers. And this is an incredibly important problem in understanding retention. It impacts finances. It impacts general business operations. And most importantly, it fits into a broader process of trying to retain your customers. So once you've identified that someone might be likely to churn, what you can do is do something proactive and reach out to them, give them an offer. Google Fiber is moving into San Francisco, and they announced this a few weeks ago, and I got an email from Comcast recently with some really great deals in it. I think they might suspect that there is a likelihood that many people in San Francisco will churn. So we have a bowl of fishes. We want to know which fishes want to sneak away. So we need to look at our customers and try and understand that given this month, what information we have about them, how we might predict which customers might not be there in the future. So looking at these 3, the president probably has some phone calls to make next month, probably is too busy to change his phone plan. Young lady, she's probably also a busy woman, a little too busy to change her phone plan. The baby might realize that it can't talk, and so a cell phone is less useful to it. And so I would suspect that, just based off features that I've extracted looking at the photos, baby's probably not going to stick around as a long-term paying customer. So I don't recommend actually using photos for churn prediction in telecoms. There's probably other data that telecom businesses have. So what I've done is this tutorial that I'm beginning to explain the process of. The data set comes from the University of California, Irvine Machine Learning Dataset Repository. It's a very large and diverse dataset repository that if you're looking for an example, highly recommend it. This particular dataset contains information mostly around the phone number of customers, where they live, the state they're in, the number of minutes that they used during the day, the number of minutes they used at night, whether or not they had an international plan, how many minutes they used on the international plan, and just a bunch of numbers that are probably useful. And then also a label. So usually if you're a telecom, you have to come up with those labels yourself. You would come up with, okay, I have the last 3 years history of my customers' information. I have a time of prediction that I want to build my data set around. And so let's look historically and say, let's use all the information we know about our customers up until a month ago. And then in the last month, if they stopped subscribing, then we'll label them as churned. And so this data set has already been formatted into that pre-labeled format. And so that's very useful and easy for us. This is going to be pretty simple. What we're going to do first is take this file, which is just a big CSV file, and read it into Spark. I've sort of lied because I've been talking about RDDs, but we're not going to read it into an RDD. We're going to read it into a data frame. And I'll get to why in the next slide. But the general mechanism is relatively easy, if verbose, where what we do first is we describe the schema of the file that we're reading in. And so this means a column name and data type, as well as whether or not the column is nullable. You make a big list. And then the call to actually create this data frame is with a Spark SQL context, which is like a Spark context, but it knows how to do SQL for you. You read it in, you tell it the format, which is a CSV format, that there's a parser out there that already exists, and then the file name and the schema. And that returns to us a data frame. So given this, we could do some SQL operations on it if we want, but that's not our goal here. Our goal here is to do machine learning. So why are we using data frames all of a sudden? The short answer is that the Spark model for RDDs and what can be contained in an RDD, which is anything, is very flexible, which is wonderful. But it also gives you enough rope to hang yourself with. And so I've definitely done this before, where for every object inside of my RDD, there might be nested objects inside of it. And I run my Spark job, and I'm like, yeah, Spark is so fast, this is going to be great. And then it's really slow. And the reason for this is that the memory overhead of creating all these objects and handling garbage collection can really put a lot of pressure on the system and slow it down. And so one way that you could solve this is to flatten out the data structures, which is fine. But at that point, when you're flattening out data structures so that every attribute that you might want has a single name within one object, that looks a lot like a row in a table. And so it's a good place to step back and think, if I have a bunch of rows in a table, maybe I should let Spark know the schema and handle that for me. Another reason that this is particularly useful from the Python side is that operations that require moving data between the JVM and Python processes are very slow. This is because the way Spark moves data between the JVM and Python processes is first opening a pipe between the JVM and the Python process. And that pipe says, hey, I'm going to write a file out here with the data that you need. So not only are you thought you were using Spark to avoid data I/O, but you were wrong. And every time that you need to move back and forth, you're going to do more data I/O. And so it tends to be pretty slow. So if you create data frames and trying to move as much of the processing that you might be describing in Python to data frames, then data stays in JVM land and doesn't have to be written back and forth. And then the third piece of why data frames, particularly for MLlib, is related to the machine learning modeling lifecycle. So if I'm going to do something simple, like create a model, there's two pieces to this. There's model training and model evaluation. And the way that we handle this and make sure that we're correctly evaluating our model is that we take our data set and we break it up into two pieces. We say we have a training set and a test set. And the test set is probably a smaller percentage than the training set. And then we have a file that contains not quite exactly what we want. Often it contains, in our case, strings, which machine learning models, even textual models, require turning strings into some type of numeric vector representation. And so feature extraction is usually the process of going from the data you have to the data you want. And so in our case, it's going to be relatively simple. But often you might want to do more complex feature construction that is actually really useful and shows something specific about an entity or individual. It helps you differentiate groups or whatever it is you're trying to accomplish in your machine learning model. So there's a feature extraction step. And then the reason that MLlib can be a library at all, or that it's useful to define it as a library, is that machine learning algorithms inside of it accept the same types of data types. So if I train a model and I realize it's terrible, it's really easy for me to go and change it to a different model or try to tweak the parameters inside of it and so on. Now, given that I've gone through this process of reading in my training set, doing feature extraction, and then training my model, I have a model that I can apply to something. And I could write it out, like serialize it in some way and deploy it into production, but that would be kind of wild, not having checked it first to make sure that it's even half sensible. And so we, of course, check it first to make sure it's half sensible. We go look at the test set, and we need to reapply the same code. So the same feature extraction step translates very literally to the test set. And given that we know what type of model that we trained, we should know how to score it, how to actually apply it to a vector. So the problem that we're presented with is that there's two places where we could be repeating code, and we could be repeating code differently. And so we want to make sure that we're always applying the same code, and we don't want to just spend all of our life writing down the same thing. And so many machine learning libraries aim to do pipelining of your models. And what this means is that you describe what the process is from end to end, your feature extraction and then the model type. And then there's two different modes that you can apply it in. One is a training mode, and one is a transformation or scoring mode. Sometimes it's called fit and transform. Who here has used scikit-learn? Yeah, so scikit-learn has exactly this pipeline concept. And this is where Spark got inspired from, because it's very convenient to wrap these up into pipelines and then apply them in different contexts. So given that we have trained our model, we've applied our model, we have results, we need to evaluate it and come up with some sort of metrics around that. And Spark MLlib also provides facilities for evaluating your models once you've scored them, or once you've scored your data sets. So let's specify feature extraction. We are working with DataFrames here, and that is because MLlib pipelines only work with DataFrames. There are two packages inside of Spark MLlib. One is called MLlib, which works on RDDs, and the other one is called ML. I'm saying I'm talking about MLlib because everyone calls both of them MLlib. So excuse my imprecision. What we've done here is we've created our data frame, we've loaded it in, and now we need to specify what our feature vectors look like and what our labels look like. And I've already pointed out that some of the information that we want to use is in the form of a string, which is not that useful to us. And so we can keep our numeric columns. Those are already floats or doubles, and Python will just handle it. And then we also need to transform strings into numeric values that Spark can handle. And so there are things called string indexers, which Spark already provides, which will look at the strings that are inside of a column and assign each unique one a new numeric value. This is great. We have two values inside of the label indexer, yes or no. Did they churn, yes or no, 0 or 1? And similarly, the plan indexer, do they have an international plan or not? And so we tell them what our input column is, just the name of the column, output column, and we put these together. So the vector assembler is how we take multiple columns and create a feature vector out of it. So we go from having columns that have single type schemas to a column that has a vector inside or a reference as a vector inside. And we also need to say what our labels are so that we can either use it for training or use it for evaluating whether we're right or wrong once we're done. Given that we've done our feature extraction, I've cleverly mislabeled this slide to help you understand that what we're going to be doing here is actually model training. So we've picked out the model that we want, which is going to be a decision tree. And we tell it where the labels are coming from and where the features are coming from. Decision trees are really simple. They don't require any parameters. But another aspect of this pipelining that's really convenient is that you can also do hyperparameter optimization relatively easily using these pipelining mechanisms. So we've got our feature assembly steps. We've got our model training or scoring steps, and we define a pipeline. So what we do is we just give it a list of the operations that need to be applied in the order that they need to be applied. Notice that the assembler from the previous slide requires first that the string indexing has happened. So here we say, do the indexing, assemble the feature vector, train the model. Then we split our input data sets into training and test sets, and we can give this data frame to our pipeline and have it fit a model, and then we'll apply it on the next, in the next phase and actually see what the evaluation metrics are telling us about it. So pipeline.fit of data. Great. So we've got a model. We now need to evaluate whether or not this is any good. There are many different ways that you can be wrong in machine learning. It's really important to understand the variety of ways you can be wrong. And two very important ones that come up when you're thinking about classification are the true positive rate and the false positive rate. I always think sensitivity and specificity are very harder to understand than true positive and false positive. So the y-axis is true positive rate, x-axis is false positive rate. And the way that these curves get created is that, let's imagine that you have a model that outputs a continuous number between 0 and 1, and your classification scheme can choose a different threshold under which it's class A, over which it's class B. As you vary that, your statistics about what your true positive rate and false positive rate are going to change. And so I think it's easiest to understand this graph in terms of the extreme cases. If we had a perfect model that immediately had a perfect true positive rate and no false positives, we would have a line that looked like A. If we had a completely random model that the true positive rate to false positive rate trade-off was always about the same, then that's like that diagonal line C that we see across it. Realistically, we're going to have something that looks like B. And you can kind of look at it and be like, yeah, that's a good shape, I guess. I don't know. That's a method. A more standard method is to look at the area under the curve. And so this is called the AUROC. Let's look at these two extreme examples. We know that random guessing, which should be the baseline, is an AUROC of 0.5. A perfect model has an AUROC of 1. So somewhere in that range between 0.5 and 1 are the models that are realistically going to get used. I'd say my general impression is that 0.8, I begin to feel all right about putting a model out, depending on what the model is or what you're optimizing for. So let's look at what model evaluation looks like. Spark, of course, also provides k-folds cross-validation and hyperparameter optimization, but I'm keeping it simple, training a model, and getting one metric out. So we take our model, we transform the test set. So we now have our predictions, and then we create an evaluator. This is a binary classification evaluator. If you're doing multi-class classification, then you get one of those too, and it'll give you all the sort of right statistics about your model. And it's very simple. Evaluator.evaluate, give us predictions, and it'll print out some interesting information for us. So we trained a decision tree, and we should be comparing this to random guessing, right? So we would expect that a good decision or a good model would have an AUROC around 0.8 or 0.49. Does anyone have a guess as to why this model didn't work well? So decision trees tend to overfit. If you apply a decision tree to your training set, it'll do a good job of being very specific about that training set. And if you were to re-predict on that training set, it'd probably do a pretty good job. But its generalizability is not great, meaning that when you try to apply it to data it hasn't seen, it's too specific to the training set you already gave it. Meaning, in this particular case, if we had flipped our guesses, just taken the opposite guess, we would have done a better job. which is not a great model, which is a great segue into the tutorial, which would allow you to take the same data set and then rework it in terms of whatever model you think might be better. So a good way to solve the problem of overfitting in decision trees is to use a random forest. This is going to be relatively easy to do. Hint, all you need to do is back here, change the type of model that you're using. And so again, this is a library because it's really easy to switch out the models that you're using. So please go play around with this, see what models work best from this data set, look at the statistics. There's also some pretty interesting data visualizations and data exploration before you get into the model, and it shows you how to use an IPython notebook together with it. So that is my talk and an overview of Spark and MLlib. Do you all have any questions?
Thank you, Julia. It was a great presentation. I did want to see if you had any perspectives on the Apache Arrow project and how it might be significant for data scientists.
Oh, absolutely. So there's two related projects. For those of you that don't know, the Apache Arrow project is a movement to standardize the in-memory format of data between projects. So this is between things like Impala and Spark. And the reason for this is that what we just talked about with Python, needing to write with PySpark and communication between Java and Python processes, needing to write out files between them, is that there's a lot of overhead there. But if we were to have a standardization of in-memory formats, it would be much easier to communicate across these processes. And so there's also a related project called Apache Feather, which is the corresponding file format for this, so that it's very easy and fast to read across these systems. And so Wes McKinney has been working at Cloudera for the last year and a half or so. When I sit down in the office, he sits approximately there. And so I get to hear his updates as he moves these along. And his focus is absolutely to improve the Python experience for data scientists, specifically around these sort of gnarly performance issues. And beyond the speed impact that Arrow is going to have, which many projects have already agreed to adopt this format, actually, which is great. Apart from the speed impact, the cost of debugging and understanding the interactions of the two processes, I think, is going to go down as well. So does that answer your question? Great. Any other questions? Yeah, you can ask me any data science-y question you want. Arrow's great. I love Arrow. Anything else?
So what do you suggest to use Java, Scala versus Python?
Okay. So I don't think that there's a distinctly good answer. It really depends on what the team is that might be using it. So when I go and talk with customers and they're like, what should we be doing? Why don't I use Spark? What's the right answer? And the answer is, well, it depends on what your team's skills are and how much time or energy you want to invest in changing those skills in different ways. So when I need to write code that's going to be productionized, and it's already well defined in my mind what the solution is, what the model it is I need to apply, I will immediately start writing that in Scala. That's because I already know Scala. Beyond knowing the language, I already know all the JVM tooling around Scala. I know, Maven or SBT or all these pieces. And I think one thing that's underestimated about saying that, like, oh, our data scientists are going to learn Scala Spark, is that it's not the language that's necessarily hard. The APIs are really similar. It's relatively straightforward. The challenging part is often around the tooling and being able to actually use Maven and then deploy things correctly, understanding class paths, right? This is not something that's within everyone's skill set, nor should it necessarily be. It's a lot of work. On the flip side, Python is very accessible. Many people that are into data processing and machine learning from the statistical and mathematical side already understand Python and know how to use it. There's not a whole new huge tool set. A drawback there is that it can be very complex to understand the interactions between the Java processes and the Python processes when things go wrong. And so it's like pretty easy to write. But I think the real cost of a lot of distributed data processing frameworks is not in the API. Like, yeah, MapReduce takes a little while to write, but can you debug it well? Do you understand where things went wrong or what went wrong? When you use the Python side of PySpark, you not only need to understand when things go wrong to debug it, the inner workings of the Spark JVM world, but also how it's communicating with Python processes. And so sometimes you'll get indecipherable Python errors that you then need to go dig and find other log records somewhere else to find the right solution. And so there's trade-offs there. And this is one of the things that having Wes at Cloudera, for example, is really helping us focus on and improve what that overall Python experience looks like. And so I don't think there's a best answer. If you're doing something exploratory and you want to quickly enable people that already know Python to use it, then great, you can use Python. But there will be drawbacks. Like anything in engineering, there's sort of trade-offs. So my answer is whatever skills people have them start with that. And if they find themselves limited, then switch and learn something new.
My question was more like third-party libraries or the libraries which are built in Spark, Scala, or Python. How often they are being updated in all the three technologies?
I don't think I fully understand your question.
My question, okay, let me phrase. Suppose a new module comes. Somebody had written a committer has written a module. It might be in Python, but might not be available in Spark or Scala. Or something might be available in Scala, but might not be in Spark. So how do you,
So you mean inside of the Spark API, something gets added to one piece of the language but not the other? Or do you mean outside libraries or modules that do statistical analysis on in a single process, and then you want to be able to use those from your Spark programs? The second one?
yes, outside and inside, both ways.
Okay. Inside of Spark, what usually happens is that Scala so PySpark is not nearly as heavily developed as Scala Spark. So it is often lagging behind Scala Spark by about a version. So there's often pieces, for example, in random forest, there's a feature importance attribute that got added in Spark 1.6 that is not available in the PySpark API yet. So there's drawbacks there, but it's almost always that Scala Spark gets developed first. When it comes to external libraries, that has more to do with how you access external libraries from the different versions of Spark. So in Scala Spark, you add it to your dependencies, you make a jar, it just works. In Python Spark, you should always be managing your Python dependencies on your cluster anyway. And so if you need to have, let's say you're using stats models, which is a Python library for stats models. If you're using stats models and they update a new version, you have something in there you want to use, you need to be able to deploy that to your cluster so that it actually exists out there on your cluster. So when you do that distributed computation, you say like, hey, import this module. That module actually exists on the computer that it's trying to run on. And so that is more of an environment deployment management issue that is not easy to deal with from inside of Spark, but needs to be thought about at a higher level. And so one of the things that I've helped create at Cloudera is a parcel in which you can use from Cloudera Manager, which is basically Anaconda. If you're familiar with it, it's a scientific Python environment where all of the libraries you might want are already installed. And it's very easy to deploy that parcel via Cloudera Manager. And if you were to create your own parcels using virtual environments or modified conda-env, it's relatively easy to do. You can deploy that on your own parcel, or you can deploy that on your own cluster using Cloudera Manager. I think that answers your questions, right?
Yeah, but it does come with a lot of side effects.
It's true. But usually the side effects you want, which is the dependencies that you want are on your cluster. Yes?
What about Spark R and the MLlib libraries? Those are completely rewritten, I assume. Nothing to do with the R libraries.
Yeah, so can you repeat the question for the mic?
Yeah. Can you speak a bit on Spark R? And then the other question is like MLlib libraries. Those are like completely separate.
From Spark R, from core Spark?
The standalone R libraries. So these are Probably similar, but yeah.
Yeah, I'll talk about how Spark R works. Spark R is significantly less developed than the PySpark API. It's not something that's supported by Cloudera yet because we don't think it's in a state that it can be supported by Cloudera yet. What Spark R currently does is allow you to define Spark jobs in R, but more of the core Spark API. They've started to add pieces that look like a normal R API for fitting models, but actually are calling MLlib under the hood. And so it's doing distributed model fitting. It's not something that allows you to use R packages or R modules in an embarrassingly parallel way. So if you wanted to do something like load a time series and fit an ARIMA model to 1 billion of these, that's not something you can do in Spark R because it doesn't have user-defined functions, UDFs yet. It doesn't do distributed R execution. R is only happening on the driver node. And so this is something that would be a great addition. I think once that exists, I'm going to be really excited to use it for those sorts of purposes. But currently, it is just a sort of R API for general Spark. Usually, if people come to me and they're like, my team knows R, they want to use R, we have a ton of data that we need to fit distributed models to, what's the right tool? Usually what I will tell them is that it's a really good idea to look at H2O hexadata. It is an R API. It's not actually written in R, but it looks exactly like R. And it has a very wide library of machine learning models. And in general, I think their machine learning models are very high quality, very well documented, have a lot of options in them. And so that is another option that is you're able to use with Spark. There's even a thing called sparkling water, like H2O. Yeah, it's funny. A thing called sparkling water that lets you prepare your data for H2O model training using Spark, and then without having to write to disk, read directly into H2O's system. Any more questions? Oh, I think I'm out of time. I'll be around. Thank you very much.